All right, the next skill on your study guide that you were asked to learn was this relationship. P1 V1 over T1 equals P2 V2 over T2. This is like a permutation of the ideal gas law. It's a way for us to relate Boyle's law and Charles's law together. So what we're saying with this equation is that if we have a gas under one pressure condition, volume condition, and temperature condition, and then we change maybe the pressure and the volume, we can calculate how the temperature will change as well. So this is a great way if you've got a situation where you've got more than one variable, where you've got pressure and volume and temperature involved, and you want to see how it's changing from one state to the next. So a great example of this would be, of the application of this would be like a weather balloon. Do you remember in what context we talked about weather balloons in class? What law were we discussing? Boyle's law, right? We were talking about how a weather balloon is one volume down, on the earth when we release it, and then what happens as it goes up to a situation where there's low pressure? What does it do? It expands. It gets pretty big. Now, some people nobody said this, I was kind of surprised, but I'm sure that there were people thinking this. As you're going up into the stratosphere, pressure is changing. What else is changing? The temperature. Okay, so this is a fantastic example. The weather balloon example is a really great example of how we combine all of these together. All right, so let's have a situation here. Let's say we've got our weather balloon. Let's say that our volume of the weather balloon on the ground is 850 liters. How many significant figures are in that number that I've given? Three, right? Because there's that decimal point after that zero. So there's three significant figures. That's our volume. The temperature when we're on the ground getting ready to release our balloon is 303 Kelvin. You only have to go from Celsius to Kelvin here. I've done it for you. Great. All right, and our pressure, again, we're just going to assume right at sea level, 1 atmosphere. Okay? All right, so as this balloon goes up into the atmosphere, it's going to experience, the gas inside that balloon is going to experience some changing conditions, right? We know that the pressure is going to change. Again, does the pressure go up or go down? It goes down, right? 0.126 atmospheres. That's just the number I picked. It's somewhere, not quite in the stratosphere yet. All right? And let's say that the temperature, say it's caught in a cold stream, 273 Kelvin. It's right at about 0 degrees. So the pressure has changed and also the temperature has changed. All right, the pressure going down is telling us that the volume should increase. The temperature going down is telling us... Your alarm is going off again. Shh. Okay. I hope it's not going to go off every 10 minutes. That'd be kind of funny. Okay, it's a good timer. All right, so let's see. So our temperature now is going down. So what would that tell you perhaps about the volume if temperature goes down? What should volume be doing? Going down. So now we've got a situation where one law, Boyle's law, is predicting that the volume would increase, while Charles's law is predicting that the volume would decrease. So we can't just use, either Boyle's law or Charles's law. We've got two variables, so we have to use this combined law to find what we're looking for, which is the volume of our balloon. How big is my balloon going to get when it goes up to its cruising altitude, or whatever you call it when weather balloons go up into the atmosphere? All right, now I'm going to use this problem to also explain a little bit about how I like to attack these sort of problems. Now, when you get this problem, if you got this on an exam, it would be written out in sentences, right? It wouldn't be in sentence form. It wouldn't be kind of nice and neat like this. What I like to do when I'm given a word problem, write out all the information that you've been given, so that way you don't have to go back into the problem and be searching for numbers. It's just right there in front of you. Another thing I like to do is once I've got all that done, go to my formula sheet and pull out any equation that I might need to solve that problem. And I write it right there, right next to all of my data. So that way I'm not having to flip back and forth and look everywhere for that. And I know that you might be thinking that what I'm describing seems like it takes a long time. It takes a lot longer if you mess something up and have to go back and try to redo things. If you're methodical about this, you actually will be faster. All right, so we've got that. Great. I don't think we need any other constants. I think we're good. We're ready to start to try to solve this problem. Now, I've seen some people in class that just try to start plugging numbers straight in without rearranging the equation. I don't think that's a very good idea. I think it's best to rearrange your equation while you've got variables there and then plug in your number. We're looking for V2, so let's isolate V2. P1, V1, multiply both sides by T2, divided by T1, divide by P2. All right, so I'm going to rearrange everything so that way I can just plunk everything in my calculator. Great. Now I'm going to rewrite it adding in the numbers. And again, this is going to seem tedious, but there's a reason for this. P1, 1 atmosphere. V1, 850 liters. And T2, 273 Kelvin. Divided by T1, 303 Kelvin. And P2, 0.126 atmospheres. Okay? All right, great. Now again, you might be thinking super tedious, but this is going to do two things. Number one, it's going to make sure that I haven't messed up. I need to double check here. You guys double check me, because like I transpose numbers, sometimes I transpose these things. All right? So it's going to make sure that I haven't messed up in like what should be where in the numerator or the denominator. And it also allows me to do this, to do my unit analysis. I should end up with units of liters, which is what I'm looking for, which is volume. When I put this in my calculator, the number that it spits out should be 6078.11 liters. Is this a number that I'm going to circle on my exam as the answer? No, why not? Sig figs. How many sig figs should this answer have? 3. All right, so you could write it like this, 6080 liters. I would consider that 3 sig figs. If you want to be really not ambiguous at all, if you want to be definite about the number of sig figs you have, get rid of this trailing 0 by using scientific notation.